Hey everybody, welcome back to the channel. Today we are going to talk about uncertainty or entropy. If you are from a science background, you must have read about entropy in your physics or chemistry syllabus. Entropy measures the degree of uncertainty or randomness. In computer science, entropy is adopted from the information theory approach, which also resembles the degree of uncertainty. Let us understand intuitively what entropy represents, how entropy is measured, and what we can infer from entropy. As we mentioned, entropy measures the degree of randomness or uncertainty of a random variable. Imagine tossing a fair coin. There are two possible outcomes, head and tail. Both are equally probable. So we are only 50% confident about any outcome, or our degree of uncertainty here is only 50%. Imagine having an unfair coin where the possibility of having a head is 75%, whereas the possibility of having a tail is 25%. The uncertainty in both of these outcomes would differ, right? A very related terminology is information gain, which measures the amount of information required to make the outcome certain. Like how much information do we require to convert our uncertain 50% certain outcome for a fair coin to a 100% certain outcome? That is information gain. It is measured in bits. Bits is the computer terminology that is being used. Now let us intuitively understand how entropy can be measured as bits and what do we infer from entropy. Let us consider the same example of the fair coin. Right? We have two possible outcomes. Our event is 50% uncertain for any possible outcome. Now, in order to make the event 100% certain, we need to know the outcome. We have two possible outcomes. How can we encode these two possible outcomes? Using just one bit, right? So, our entropy in this case would be one bit, right? Similarly, let us consider another example of weather which say 8 possible states. All these 8 possible states are equally probable with a probability of 1 by 8. So how many bits are required to encode these 8 possible states? Because in order to convert our uncertainty to a 100% certain result, we need to know the 8 possible outcomes or the 8 possible states, which has to be encoded using 3 bits. So our entropy in this case would be 3 or 3 bits. But what if, as we mentioned previously, our events are not equally probable? What if our outcomes are unfair or they occur with unequal probabilities? Say a weather with two possible states with probabilities 3 by 4 for rainy and 1 by 4 for sunny. So uncertainty for rainy is 25%, while uncertainty for sunny is 75%. In order to convert an uncertain rainy outcome to a certain outcome, we need to make a jump of 4 times, right? While for an uncertain sunny outcome, we need to make a jump of 4 by 3, right? So, would you consider that the number of bits required to encode these two information would be 1 in this case? No, if you are thinking the answer would be true, then you are not right in this case. Here, the number of bits required would be less than 1 because the two events are not equally probable, and the entropy ideally measures the weighted average of the number of bits required to encode the information. Mathematically, we can see the formulation on the screen below. This is the graph which represents the entropy variation for a binary random variable, wherein the entropy for a particular outcome with probability 0.25 is 0.81, of zero point 0.5 is 1, 0.75 is again 0.81 because the event is binary, and so on. Additionally, certain points to mention here is when we are talking about entropy in machine learning aspects require uses back propagation as its primary computation method in neural networks. So in order to make that back gradient computation simpler, we use Bayes E instead of our base 2, which is used for bits. The entire concept remains the same, however, the base changes. Related term is cross entropy. However, cross entropy measures the difference among two probability distributions. It measures the entropy of the random variable plus the KL divergence between the true distribution versus the predicted distribution of the random variable. Mathematically, it is represented as shown in the screen here. I wish, I hope you enjoyed the lecture and had something new to learn. See you in the next. Take care. Bye bye. And don't forget to subscribe to the channel.